Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized pieces.
Today, we're looking at a paper with a title that sounds like a paradox: when less latent leads to better relay. The core idea is that sometimes for AI models to work together better, they should actually share less information with each other.
That sounds completely backwards. If I'm working on a project with someone, I want them to give me all the details, not a heavily edited summary.
Exactly. And that's what makes this so interesting. To understand it, we first need to talk about multi-agent AI systems. Instead of using one giant AI to solve a complex problem, researchers are now creating teams of AIs that work together.
Like an AI consulting firm, you could have one AI that's a brilliant planner, another that acts as a critic to find flaws, and a third that writes the final report.
Precisely. But for that team to work, they need to communicate. The old-fashioned way is for them to just send text messages to each other like humans do, but a lot gets lost in translation when an AI has to condense its internal thoughts into simple words.
So what's the alternative? An AI mind meld?
Basically, yes. It's called latent communication. Instead of sending words, one AI agent can send its entire internal memory state directly to the next agent. This memory is often called the KV cache.
Let's define that term. What exactly is a KV cache?
Think of it as the AI's short-term memory. As it processes your request, it builds up a context of what's been said and what's important. The KV cache is that context. By sending the whole cache, the receiving AI can pick up the train of thought exactly where the first one left off, with all the nuance and context intact.
Okay, so this mind meld, or KV cache relay, is a much richer way for AIs to communicate. But I'm sensing there's a catch.
A very big catch. This KV cache, this train of thought, is enormous. Relaying the full cache for every step of the process consumes a huge amount of memory and bandwidth. It's like trying to send a full-length, uncompressed 8K movie just to share a single idea. It's slow, expensive, and just not practical as these systems get bigger.
The obvious solution then is to compress it, right? Just send the most important parts of the memory and discard the rest.
That's the starting point, but the authors of this paper took it a step further and discovered something remarkable. Not only did compressing the KV cache save a ton of resources, we're talking reductions of 80 to 90%, but in many cases, the AIs performed better with the compressed information.
Whoa, so less really is more. How is that possible?
The researchers suggest it's a form of denoising. The full KV cache contains every single detail, including a lot of noise and irrelevant information. By selectively keeping only the most important parts, you're basically giving the next AI a cleaner, more focused signal. It doesn't get distracted by the junk.
That makes sense, but it puts a lot of pressure on the compression method. If you throw away the wrong thing, the whole project could fail. This is where the paper introduces its main innovation, right? A new technique called orthogonal backfill, or OBF.
Yes, and this is the really clever part. Just throwing information away, which they call hard eviction, can be risky. You might lose some subtle background context that's not obviously important, but still useful. OBF is a way to get the best of both worlds.
All right, break down orthogonal backfill for us. Let's start with an analogy.
Imagine you're packing for a trip with a tiny suitcase. You can only bring a few essential items. Those are your retained states, the information you're definitely keeping. You have a big pile of clothes you have to leave behind. That's the discarded information.
Okay, so far so good. I've packed my essentials.
Now, instead of just leaving that pile of clothes, OBF says to look at it and figure out its unique essence. Maybe all the clothes you left behind have a specific bohemian vibe that isn't captured by the formal clothes you packed. Orthogonal backfill finds that unique leftover vibe. That's the orthogonal part. It's the information that is totally different and independent from what you kept.
And the backfill part?
You then create a tiny summary of that vibe, like taking a single photo of a mood board for that bohemian style, and you backfill it or tuck it into your suitcase. So now you have your essential items plus a tiny compressed reminder of the useful context you left behind.
So in AI terms, OBF identifies the information to be deleted, extracts the parts of it that are truly unique and not represented in the kept data, and then injects a tiny summary of that unique information back into the message being sent.
You've got it. It's a way of saying, here are the most important details, and by the way, here's the general gist of everything else we talked about, just in case you need it.
And the results prove this works?
The results are pretty stunning. They tested this on 9 different benchmarks, things like complex math reasoning, code generation, and medical question answering. The OBF method achieved a communication cost reduction between 80 to 90%, and on 7 of the 9 tasks, it was the best performing method overall.
Better than even the method that sent the entire uncompressed KV cache?
Yes, even better than that. It confirms the less is more theory. By sending a compressed, denoised message that still cleverly retains the essence of what was discarded, the receiving AI agent had a clearer, more useful signal to work with.
So the big takeaway here is that for AIs to collaborate effectively, the goal shouldn't be to send more information, but to send the right information. It's about quality, not quantity.
Exactly. This paper shows that intelligent compression isn't just about saving memory, it's about actively improving communication. By filtering out the noise and preserving the most useful signals, we can build AI teams that are not only faster and cheaper, but smarter too.